Today, we're going to talk about a system that's pretty much invisible, but it runs a huge amount of our physical world. I'm talking about Modbus. It's an industrial protocol from way back in 1979 that just, well, it refuses to die. It's really the unsung hero of the factory floor, letting millions of devices speak a common language. And that, right there, is the central mystery we're diving into. I mean, we've got protocols that are faster, way more secure, packed with all these modern features. And yet, Modbus just hangs on. So our mission today is to figure out exactly why this relic from the 70s is still so darned essential. Let's kick things off by looking at where it actually lives in the digital world. At its heart, Modbus is what's called an application layer messaging protocol. Now, I know that might sound a little technical, but where it sits in the whole networking stack is actually the first big clue to its incredible staying power. See, by sitting all the way up at level 7, the application layer, the protocol becomes completely media agnostic. To put that a different way, Modbus really doesn't care how a message gets there. Could be a radio wave, a copper wire, a fiber optic cable, whatever. It only cares about what the message says. This genius move, separating the command from how it's delivered, is the first secret to its long life. And this flexibility is exactly why it's still around. It can run over classic, old-school RS-485 serial wires, the environment it was born in. Or it can be wrapped up in a standard TCP/IP packet and sent over modern Ethernet using the reserved port 502. The commands themselves are identical, but the delivery methods can be literally decades apart. So while the protocol itself is flexible, the rules of communication are, well, they're anything but. On a noisy factory floor, you just can't have devices talking over each other. It would be chaos. So to prevent that, Modbus enforces these incredibly rigid rules on a serial bus through a strict master-slave relationship. This is the perfect way to think about it. The master is the traffic cop. It's the only device that's allowed to start a conversation. It's always the client, always sending requests. Every other device on the network is a slave or server, and they're only allowed to speak when they are explicitly spoken to by the master. This completely prevents message collisions. It's just that simple. But there is one exception to that speak when spoken to rule, address 0. This is broadcast mode. The master can send a single write command to every single slave on the network at the exact same time. Now, here's the catch. No slave is allowed to respond. So you gain this massive efficiency, but you totally sacrifice confirmation. It's a high-stakes tool, really, used for critical commands where you just can't afford the delay of waiting for a bunch of responses. So what does one of these messages actually look like? The best way to think of it is like a registered letter. The core message is called the Protocol Data Unit, or PDU. That's the actual instruction, the content inside the letter. This then gets wrapped in the Application Data Unit, or ADU, which is like the delivery envelope. It adds the slave's address and an error checking seal, something like a cyclic redundancy check, or CRC, to make sure it arrived intact. The PDU is the what, and the ADU is the how and where. And what if something goes wrong? This is where the design is just beautifully simple. If a slave can't execute a command, it doesn't send back some complex error message. Nope. It just takes the function code it received, flips one single bit, the most significant one, and sends it right back. It's an incredibly fast, byte-level way to just raise a red flag. Okay, so we've seen the message structure. Now let's look at the data itself. The absolute core of Modbus is its incredibly simple fixed data model, and it's organized into 4 distinct tables. This whole structure is key to how the protocol enforces integrity. The entire data model is built on this really elegant structure. You only have 2 types of data, single bits and 16-bit words we call registers. Each of those is then split into 2 groups, read/write and read-only, and that gives us our 4 tables. Coils are bits you can change to do something, like close a valve. Discrete inputs are bits you can only read, like a switch's status. Holding registers are variables you can change, like a temperature set point. And input registers are measurements you can only read, like the current temperature. The protocol itself enforces these permissions. It's baked right in. Now, beyond just simple reads and writes, the protocol has some incredibly efficient advanced functions. For example, read/write multiple lets a master do 2 things at once, like writing a new temperature set point and reading back the current pressure, all in a single transaction. This is huge for cutting down network latency. Then you have something called mask write, which is basically like performing digital surgery. It lets you change just one single bit inside a 16-bit register without touching the other 15, which could be critical for status flags. All right, here's a quick but super important detail that trips up engineers all the time. Modbus is big end in. This just means that when a 16-bit number gets sent across the wire, the most significant byte, the big end, always goes first. It's a classic source of bugs when you're connecting different systems, and a perfect example of the kind of low-level details you have to pay attention to with this protocol. So we've built the message. Now we've actually got to get it across the wire. And this is where Modbus gets extremely specific about timing, which brings us to its two different transmission modes. Every single device on a serial line has to agree on one of these. RTU is the default, and for good reason. It's fast, it's efficient, and it packs data tightly in binary. ASCII mode, on the other hand, is much slower and sends human-readable text, but it's way more forgiving on timing, allowing up to a 1-second gap between characters. It's a classic engineering trade-off. Do you want speed, or do you want forgiveness? To really understand RTU mode, you have to get its obsession with timing. This right here is the golden rule. If a receiver detects a silent gap on the wire that lasts longer than 1.5 characters during a message, it doesn't wait around. It assumes the message is corrupt and instantly throws the entire frame away. And then, on the flip side, the system requires a silent interval of at least 3.5 character times between messages. That silence isn't just a pause, it is the signal. It's how devices know for sure that one message has ended and the next one can begin. This strict time-based framing is exactly why you need reliable deterministic hardware to run Modbus properly. And you absolutely cannot ignore the physics. For stable RS-485 network, there are two non-negotiable rules. First, you have to install terminating resistors at both physical ends of the cable to stop signals from bouncing back. And second, if you need biasing resistors to prevent noise, they have to be applied at only one single location on the bus. Get either of those wrong, and the whole network just fails. So, after looking at the application layer, the message structure, the data model, and those super strict physical rules, we can finally answer the question we started with. Modbus succeeded, and it endures because it is deterministic and it is simple. It's a reliable protocol built for environments where noise and timing are your biggest engineering challenges. It's industrial networking that's based on physics, not a bunch of complex software layers. Which brings us to a final thought I want to leave you with. Modbus has these built-in diagnostics that report really granular physical errors, like bad checksums or character overruns. As we move to modern abstracted networks, like Ethernet, where that physical layer is hidden from us, how much diagnostic depth are we sacrificing? Does the convenience of modern networking justify losing that immediate low-level insight into why the communication actually failed?